and coffee, of course. When we dip the napkin in the coffee, we see that the fluid rises up through the napkin because of capillary forces. These capillary forces appear here because the napkin is a porous medium. That is a material which contains several porous or little holes. These little holes make the force that pulls the fluid into the napkin. That's why it rises up. And these little holes are randomly distributed within the napkin. So this pulling force is random. So the force that fills the interface is random. And the competition between this random force pulling the interface up and the forces that try to make the interface flat, that are the surface tension and the viscosity, this competition of forces give rise to this, this draft interface up here. So this whole process is an example of a kinetic roughening process. Yeah. Of course, in the lab, I don't work with coffee and napkins. It's about to finish, yeah? Don't worry. Of course, I don't use coffee and napkins. I just drink the coffee. But instead, I use this experimental system down here. Rather than using a cup of coffee and coffee, I use a syringe pump with silicone oil. And instead of a napkin, I use this model of porous medium that consists of two parallel plates separated a narrow gap, where in between I put some obstacles randomly distributed, simulating these porous we have in napkins. Then I inject the oil through the system, and I record from the top the evolution of the interface. This is a typical image I get in my experiments with the interface marked here in red. For the ones familiar to this kind of system, this is the interfacial equation with the pulling forces here, the surface tension term that dampens the interface, and the perturbation and the viscosity term here. This interface, regarding its morphology, can remind us several other surfaces we can find in nature or even here. If you look at this surface here, it's quite similar to this one, which is a self-affine structure. It can also remind us of this one up there that corresponds to Montserrat. But I'm not interested in the morphology of the fronts, but in its dynamics. Specifically, I'm interested in the characterization of the intermittency of this process, the spatial and the temporal correlations. In order to do so, we can perform several analyses. For example, in the local scale, we can plot the local velocity map. This is a part of my porous media, and in this gray scale, I plot the velocity, the darker, the slower. So here we can see that at some points, the interface just gets stopped, and then it moves really fast afterwards in these white spots. These events are local avalanches. We can also see these avalanche dynamics when we look at the global signal here. Here I plot the mean velocity of the front as a function of time. We can see that this is a really jerky, bursty signal, where we can define also avalanches, study their properties, the size distributions, time distribution, so on and so forth. And finally, we can perform a turbulence-like analysis. Maybe if there is anybody working on that here, I would be really interested to talk to him or her. But well, I won't go any deeper on any of these plots. If there's anybody interested, we can just talk during the coffee break, or you can contact me via mail, Twitter, or whatever. So thank you for your attention, and a special thanks to the organizers of this such a beautiful event.